So, hello everybody, and very welcome to our speaker, today's speaker, Tomasz Miś from Poland. He comes from the Student Space Association Wood, and he will talk about designing a rover for an analog Mars mission. You may start your lecture and have fun.
Okay, thank you very much. Thank you very much for the introduction and welcome, dear listeners. On this presentation, I shall talk about, designing a rover for an analog Mars mission, a designing done by a team of students, so not yet space professionals, but people who learn by doing an actual space project, which becomes more and more sophisticated as the years go by. Student Space Association has a very long tradition of designing not only rovers, but also other space-related equipment and projects. So observing how it evolves during all these years of our activity is very interesting and shows very important progress that is acquired by the students as their experience. So yes, the Student Space Association WUT is Warsaw University of Technology, was established in 1996 with first activities dating to 1994, and its activities are grouped to four main divisions, let's say, four main types of activities. We are building rockets for a very long time. We built students an European fastest rocket that reached nearly Mach 3. We are building satellites. Polish first satellite is a satellite from our association, that's PWSat-1, launched in 2012. We are building rovers since 2008, so it's a lot of years now, and we're launching domestic stratospheric balloon missions, and we take part in larger stratospheric flight campaigns like BEXUS projects. So yes, the association itself is very, very complex, almost like a space agency. There are lots of similarities also with the funding of the projects and public relations and so on. So this is also a very good experience. And the Mars rover project is only a small part of it all. It is located here. The SK Robotics, so the division devoted to Martian and a little bit of lunar robotics, was established in 2017 after some other projects related to Mars exploration concluded. We are currently focusing on University Rover Challenge, European Rover Challenge, and Indian Rover Challenge. So our designs compete with other teams from all around the world to prove which one is the best fulfilling the tasks related to an analog Mars mission. In the past, what we did is an actual analog Mars mission at the Mars Desert Research Station in Hanksville in Utah. It was done with the Exorion Foundation in 2017. The simulated astronauts actually used our rover as their field equipment when they were traversing the Martian-like fields in their simulated astronaut suits and so on. NASA Lunabotics was one-hit wonder, actually. In 2013, unfortunately, we stopped building lunar rovers as non-US teams were banned from these competitions. MATE competition is for submersibles. We decided to get into submersibles as they are similar in control to spacecraft, and the exploration of undersea environment is also quite interesting in the perspective of exploration of, for example, Galilean satellites and other celestial bodies like this. So it was also an interesting part. Nevertheless, Mars rover projects for rover challenges since 2008, we started building it. Two main competitions throughout the years, the European Rover Challenge and the University Rover Challenge since 2010. Not every year, with some gaps, some with moderate success, some with larger success. Nevertheless, loads of iterations, loads of people interchanging every year. and lots of experience to gather and to manage as well. Mars rover generations that we've been through were started in 2008, where the very first prototypes, very crude ones, were built. They later evolved into the first true one in 2010, the Scarab rover. It was rather small. In 2014, when the European rover challenges started, we had the second generation of rover. Then our biggest one, which still survives, it is not constantly used. However, it is practically ready for service. It was in 2015. And the current generation, which is active for a couple of years now, and is actually being right now substituted with another new design, as when people are coming into the project, they have to be educated in designing a new rover, not only maintaining the one that was designed before. So it is very important to build new ones and not only do something with the ones that were built before. The team structure that is designing Mars rovers is rather simple and rather intuitive. We're covering the mechanics, electronics, and communication, or the so-called Elcomsoft team. Software combined with autonomy, science team, very large, and the management and public relations. Also the relations with the university regarding funds and so on, so on. Our team is composed mainly of younger students, bachelor degree students. We have only 2 PhD candidate students, including myself, actually. In comparison to other teams, we do not have many skilled young professionals, many skilled young scientists to take part in this project. Our team members, our students are rather young and come into the project to learn basics, learn teamwork, learn working under stress conditions, which for the challenges, the competitions, this happens all the time, and it is very crucial to be able to work in these conditions, and of course to gain a lot of new experience, which may be useful in their later activities for master thesis or even PhD thesis. I'm not doing my PhD thesis in Mars rover robotics, but the other student, PhD student in our team, is doing his PhD work in the field of Mars rover design. So yes, it can evolve like this as well. And in other teams, it does quite often. For many, many years, we've been using numerous digital work and management tools, and this also evolves with our activities, with the project itself. First, as also other divisions in our association, we decided to separate private and project or work communication channels. This means that Facebook is almost entirely for our private talks, but everything related to our work must be done somewhere else. Luckily, our university, especially during the pandemic, gave us a lot of digital tools like the Microsoft Office tools to work remotely. We also this year changed our platform from Slack to Discord. I know that Slack is very popular, and it was in fact in our association as well. However, there were some issues with data management in Slack. So we decided to switch on to Discord, which also performs very good online meetings. So like today during the pandemic times, it is crucial to have it running smoothly. We are still awaiting something like a documentation standard, because still the robotics division in our association does it in not a very standardized way. Other divisions do it under certain standards, especially the balloon division and the PWSAT project. However, the Robotics, they are still waiting for it, and I expect it to happen in the next years. What have we also presented that we implemented in our project is the V model of the implementation and development of the elements of our designs of our rovers. Loads of testing, loads of iterations to make the elements go maybe not perfect, but running smoothly and running without major problems. We are more and more basing on the simplified ECSS requirements, constraints definition, and testing, which is also related to what our other divisions do, especially the balloonists, which do BEXOS projects, BEXOS stratospheric projects, which are largely based on ECSS documents. These standards allow us to come smoothly through the procedure of making the element go work perfectly without major problems. The implementation of these procedures wasn't that difficult as we expected, and yet these procedures are crucial in the space, not space environment, but if someone wants to work in space industry. So yes, it is good to have it implemented already. The software we use is mainly from our sponsors or the university. However, mainly they are sponsored, like the ANSYS software or SolidWorks. Luckily, our MATLAB skills have shown that we do stand above others, luckily, and one of our team members received an award for using MATLAB to implement Rover-based projects. So yeah, it is quite sophisticated, and we are getting more and more fluent in that. So getting deeper into the design of the rover itself, we have the design split into a couple of parts. First design is the mechanical design, the vehicular design. So as we call it, the mobile platform. So this thing that is used to put everything on the electronic systems, communication systems, and the manipulator. Everything here is grouped into a single team. As it evolved, it started with the most obtainable materials and mechanisms, very crude and very simple. It allowed mainly prototyping, not really building a final rover, final design, which was able to compete in the 2010 European Rover Challenge. However, in 2010, the project grew and elaborated designs were implemented. To choose some components which were commercial off the shelf, the then team decided to use the components of vehicles for the handicapped people, which was quite maybe not strange, maybe a little bit strange. Nevertheless, the components proved to be very, very robust and can still be operated today after many trials and many ordeals. In 2014, a completely new team changed its approach to design by using very widely using system profile technology, which resulted in a design which was quite cubic, quite simple, very easy to modify. However, it lacked skills in engineering certain components because it was all made almost like a do-it-yourself project. This is not what we wanted to achieve finally when we decided that the project was ready. It was just a step towards something better. This something better came in 2015 when we went back to elaborated designs using CAD, using CAE. We decided to increase the vehicle dimensions, which practically resulted in one of the world's largest student-made analog rovers. Its maximum weight was 56 kilograms. It was not the maximum weight among such rovers at all, but its overall dimensions allowed it to traverse many different obstacles, and we were able even to ride on it like on a motorcycle. So it was it was amazing. Nevertheless, its dimensions were problematic when it was to be transported somewhere or taken somewhere even at our university. So again, in 2014, we created a requirement of fitting inside an elevator. Very simple, very nicely pronounced. Nevertheless, it resulted in about 1/3 reduction of the vehicle dimensions and mass. So it was a very good decision that we took. This vehicle is still used today, the one from 2018. It is to be substituted this year or next year with a completely new design. However, this requirement of fitting inside the elevator is to be maintained for purely practical and financial reasons. The mechanical design evolution by itself is, of course, also related to the base of the components and workshops that we have carried out, we have created during the many years of our operation. Of course, the extensive use of CAD and CAE for many years, we have improved that, and practically nothing is being built and designed without it. So it is very good. As the knowledge becomes somehow accumulated, gathered, we decided to create a dedicated course on the vehicle mechanics, dynamics, and suspension design to our students. Many teams, throughout all the years of our activity, many teams from other countries have also asked us what are our, let's say, sources. I'm not saying Intel, but sources, how to design such things. And well, it is our R&D, so we're not really keen to share it. Nevertheless, among us, we do have such courses when we talk about the designs we have created by ourselves and the designs of the rovers that are real, that have been built and flown to other celestial bodies. I mean the lunokhod generation, for example, the real 3 lunochods and the test lunochods, which were tested on Kamchatka deserts. We look also deeply into automotive designs, especially by Automobile Citroën, which are the cutting edge technology of suspension design still even today. We do like experimenting with mechanics. Time for developing mechanics for a student competition is not that long, but long enough to make such new and experimental, from our perspective, experimental system fully operational. So our mechanics may be strange, may be very innovative, may be experimental, but throughout the years, we managed to make it fully operational almost every time we design something new. The manipulator, so the thing which grabs things on the ground, which manipulates with switches and knobs, which assists the astronaut also with holding and grasping tools, has been designed since 2014. The first rovers didn't have it as they didn't need it. There were 5 designs since 2014. Less elaborated, more elaborated, up to 5 stages, so 6 degrees of freedom. That's a lot, and this required lots of skills from the operator, maybe even mastery from the operator to move it smoothly. We had an aim of creating a so-called library of effectors for gripping, drilling, and electrical measurements. The fate of the effectors is that they are all the time being redesigned, rebuilt, and new effectors are built almost every year. So this is the part of the rover which is most frequently changed, not the wheels, not the electronic systems, not even the manipulator itself, the effector, the robotic hand which grips, which measures. This is the thing which is mostly changed. One of our dreams, which we want to implement, but for younger students, bachelor students, it is still not very easy, is the inverse kinematics. Other teams, other Polish teams do have inverse kinematics, but these teams are usually composed of more experienced students, of PhD students, which are doing it for their PhDs. Younger students have more difficulties with that. However, we are getting more closer and closer to inverse kinematics. And when we finally, in the upcoming few years, finally implemented, a lot of problems with the manipulator control and its coupling with the autonomy system will vanish. The electronics and software is the part of our rover which is most faulty, I may say. Some people from my team may not really agree, but from the overall perspective, especially from the perspective of many, many years of Mars rover project development at our association, the most faulty part of the system are the electronics and software. Between 2013 and 16, we received a huge amount of industrial automation components, which was practically mastered by the then team, which operated it very successfully. We wanted to implement the NVIDIA Jetson computer, however, it proved completely inappropriate for this. This was quite a huge fail because this computer was quite expensive. Nevertheless, we decided to switch NVIDIA Jetson to the autonomy processing, and this was perfectly successful. It's working still today very, very nicely. Between 2016 and 18, we sadly had to retire the industrial components except for the antennas. This retirement was caused by the fact that in our team, students do change. We have a very high rate of rotation of our team members. So the team members who mastered the industrial automation simply finished their studies and went away. They tried to pass the knowledge to another team. Nevertheless, it wasn't done perfectly, and the industrial automation components caused a lot of issues in operation. It also simply got older, and some of the components were failing during the operation on the field during the competition, so it was unacceptable at all. We decided to reintroduce some smaller platforms like the Raspberry Pi, like different kinds of motor controllers, for example, not the ones from the sponsors, not the industrial ones, that's something different. It started to work very good. Since 2018, we're employing or trying to employ STM32 platforms, which are even more into space environment. Again, the balloonists, Bexos projects, high altitude stratospheric balloons, all STM32, very strong, powerful platform, which allows us to do a lot more than before on a Mars rover. The autonomy system is also a subject of numerous modifications. However, recently it was also a subject of an award given to one of our team members by MATLAB, as our autonomy was very complex, and in MATLAB it worked very, very nicely. Image recognition, code recognition, sample recognition, it works very nicely. We usually use cameras to perform these tasks. Secondary sensors are IMU and ultrasonic. Ultrasonics were used in 2015, 2016. Right now, we mostly rely on the cameras. The scientific instruments, of course, they are mostly implemented on the rover to fulfill the requirements for the challenges. However, we do like experimenting and putting very strange apparatus on the rover. We're doing many things for the soil measurements, but also gamma vision, infrared, UV, and radio range monitoring cameras, pneumatic sample collection, drilling, multiple mechanisms of drilling we have implemented since the many, many years. What we are preparing for is the adaptive beaming for the ground station, magnetic subsurface scanning, Valdemar Poulsen's evolution, and a three-dimensional goggle-less vision inside the ground station. This is going to be extremely useful for the operator. Yes, and these are some examples of our strange apparatus on the rover. Lots of experiments and also lots of experience. There have been many issues during our project development, of course. Nevertheless, we come up constantly with solutions into it. So we are also learning by doing, which is quite crucial, especially when passing the knowledge to another students. If something like this happens, we are not forgetting it. We do record how it happened, when it happened, what was to blame, maybe not who, but really what was to blame, what is to be improved. And many of these issues, many of these problems do not repeat. This is, of course, all of it is very, very clever. We are not, however, scoring the first places. Our team is very young usually. Nevertheless, we do have our maximum, our highest place at USC is the 7th place of SK Robotics predecessor projects of Ares. And last year we scored the 4th place at European Rover Challenge. This is very high, and we hope it's even to improve in the future. In many our projects at our association, the outreach program is mandatory. So we have also a special cell in our team to manage that. We are managing it successfully. We have gathered a huge recognition in Polish media. So it's very good base, not only to promote ourselves, but also to promote us in the among the future students and future candidates for our next projects. Of course, scientific conferences with all the scientific instruments we create, they are also present here. The most recent one is shown below. That's the CESA, spelled differently, Conference on Space System Engineering at European Space Agency. Quite a success. We are trying to also educate our students when in a professional presentation of their scientific achievements. So thank you very much for your attention. I hope you liked it, and I'll be happy to answer any questions. Thank you very much.
Yeah, thank you, Tomasz, for the interesting lecture, and feel free to ask questions in the chat. I will read the questions and forward it to Tomasz. Are there any questions? Someone is asking, Archie is asking if you can share the presentation, for example, in Slack or somewhere.
Yes, I think I can share the presentation, absolutely. If there's a mean to do it, yes, I think there shouldn't be any issue with that.
Or they can email you directly?
Yes, as well. Also, you can email me directly and I can email you back the presentation, of course.
Another question is, what were the biggest electronic challenges building the rover?
Communication. It was definitely handling the communication. Handling the communication with the rover so that the rover is immune to interferences, especially during the European competitions, which are not held on a desert, of course, but they are held inside in a city. And there are lots of spectators all around us, lots of media, lots of cameras, lots of transmission equipment from the TV stations. So making the rover immune to that was crucial, reducing the delay between the rover and the ground stations. It was extremely difficult to achieve in the first years, and we have finally implemented more than one communication system, which made it safe, made it to run more smoothly. And yes, it was the communication issue, because even if all the electronic systems on board the rover do run perfectly, if we cannot communicate with the rover, it just stands still, does nothing, and we're very angry because something is not working. It's the communication. In our case, of course.
Peyton is asking, what was the hardest part of building the final design, engineering-wise?
The hardest part of building the final design, actually, it was the integration of everything. It was the combination of all the component requirements. Every component needs something very, very specific. And to satisfy everybody, both the wheels, the propulsion system, the frame, the electronics, which must fit inside the frame, the manipulator, which has a certain range to operate in, the communication, which has to connect somehow with the rover using antennas, which are to be affixed somehow. So combining all this was, I think, the hardest part, because it's required very high degree of cooperation between all the teams. We do like tinkering with our own like wheel design or suspension design or gripper design or something, but we must not forget that there are others and we must communicate with them to avoid issues. There have been such issues during our activities for these many years. However, so yes, making contact with the others, communicating what we are doing to others and knowing what the others are doing so that everything can be joined into a single successful project.
Yeah, it seems communication is a main problem in this project. Adam is asking what types of motors and batteries work best for this application?
Well, here the batteries have not just the requirements of the Mars analog mission, but also the requirements related to their transportation. As for example, lithium polymer batteries are difficult to transport on an airplane. And if we are situated in Poland, we have to go to United States. It's a very long voyage. We have to take these batteries with us. So how do we do it? We decided in 2014 to use lithium-ion special batteries, which were designed for us. They are quite light, have high power density, they're quite quickly charged, and provide the best performance we can get. If there is a smaller equipment on the rover which requires slightly different type of battery, then we may use it as well. But the main source of power are the lithium-ion batteries, which can be stacked. The motors, the prototypes 2008 use simple electric drilling motors. They were not very elaborated. However, later we switched to BLDC motors, industrial motors, mainly from Maxon. They are very expensive, but this quality really stands out. They are very durable. They have not failed us, and they are also easy to control. So yes, brushless direct current motors.
John is asking, has your group attempted any in situ resource utilization experiments on board the rover, mining ice or converting CO2, for example?
Not really. We haven't yet dealt with the CO2 as we are in the field. We are limited to the requirements of an analog Mars mission. So it is not a perfect Mars. We do not have a perfect Martian atmosphere regarding its pressure, composition, and temperature. So building, for example, sufficient thermal insulation for the electronics, Martian-like insulation, is not relevant to these conditions, as it is simply it won't work because we are still on Earth. So converting CO2, we are not there yet. We didn't build it, mainly because we cannot test it on Earth during this competition or an analog Mars mission on the MDRS. However, things like radiation, for example, radiation monitoring or humidity measurements or soil scanning, yes, we can do it both on Earth in these analog conditions and on Mars. So we decided to implement these experiments. Mining ice, still, it's the same issue. On Mars Desert Research Station, we cannot really do it. We would have to take the rover somewhere where we could actually make it drill, allow it to drill into the ice, or create an artificial block of ice to drill in. And it is still a bit too much for us. We are concentrating on building experiments which can be launched in these terrestrial analog Mars conditions. So it's unfortunately, yes, it excludes some crucial Martian experiments like the CO2 issue, or yes, temperature and pressure shields for the electronic systems and so on. Everything related with ice to ice. Yes, it is crucial for Mars, but we cannot test it in our conditions. So we haven't done it yet, at least yet.
Thank you so much. Are there any other questions? If not, I would like to close the lecture because attendees are leaving to the next lecture. So I would like to say thank you very much for this lecture and goodbye.
Yeah, thank you very much. Goodbye.